let's look at adding fractions. So in these pictures, you see the first one is there's 3 parts coloured in from this circle which has 8 bits in it in total. So it's 3/8. That's what that picture is showing. It's being added to another circle where 2 parts are green out of a total of 1, 2, 3, 4, 5, 6, 7, 8. Didn't put dots on them all, but that's what we're doing. 3/8 plus 2/8. You can see the answer. It has 5 green parts. 5/8. So what we have done here, 1, 2, 3, 4, 5 out of 5, 6, 7, 8. What we've done here, we've added the tops and we haven't added the bottoms. That's basically what we've done. We've added the tops are called the numerators, the bottoms are called the denominators. We've added the tops and we've left the bottoms the same. And that's what you do with simple adding fractions. You add the tops, you leave the bottoms the same. I'll give you a different example. Let's say we had 4/10. There's no picture for this one, but you'll get the idea. 4/10 plus 5/10. If the bottoms are the same, then they're just going to stay the same. And you just do 4 plus 5 is 9. I actually call these the easiest question in the SATs. If you're in year 6, they're not a nice, easy question, because if the bottoms are the same, they just stay the same, and you just do 4 plus 5 is 9. Very easy question. It's the same with minus. 8/12 we could have. Take away 4/12. If the bottoms are both 12, the answer is going to have 12 on the bottom. 8/12 take away 4/12 is 4/12.
One question I get regularly is, why do those denominators stay the same, Mr. Sewell?
Well, for that, we would look back at the same picture, at the first example. Why do the denominators stay the same? Because in the first picture, we have 3/8. We add it to 2/8. You can see that we've now got 5/8. It's like 3 dogs plus 2 dogs is going to be 5 dogs.
Yeah.
Or 3 burgers plus 2 burgers is going to be 5 burgers.
Yeah.
We're not changing the unit. An eighth is just a thing, like a dog or a burger.
Yeah.
That's all it is.
I always said the denominator is not the actual amount. It's a possibility. So whatever the possible amount is to create one whole, it would be that amount.
So let's concentrate now on adding fractions, and we'll do more than just the easiest question in the SATs. I keep saying SATs. I know you might not be in year 6. The easiest question in the test, I think, is when the bottoms are the same on these fractions, the denominators are the same. You know the answer is going to be in eighths. 5/8 plus 3/8, that's actually 8/8. You've actually got all the eighths, which is the same as 1 whole 1. But we're not doing that in this video. 5/8 plus 3/8 is 8/8. So that is what I call this A. That is the easy version of adding fractions. Now I'll move on to the medium version of adding fractions. I'm going to do a few examples of all this because you need to see a few examples to get this probably.
Yeah.
Sometimes the bottoms are not the same. So you may get 2/5 plus 3/10. So when I look at this question, I immediately see a problem. And the children in my class sometimes say, Houston, we have a problem, like the astronauts say if something's wrong with their spaceship. What's the problem, astronaut? Our bottoms are not the same. That's their problem. The bottoms are not the same. 5 is on the bottom here, 2/5 plus 10 on the bottom here, 3/10. 2/5 plus 3/10. We can't actually add that together. It's like adding 2 cats to 3 dogs. You can't get an answer in cats or dogs.
Yeah. The very simple solution, the very simple answer to that is that when the denominators are different, so 5 and 10, the numerators it doesn't really matter what happens to the numerators because the size of the pieces are not the same. So while that 2/5 and 3/10 might be comparable in some way, you can't add them together because the sizes are different.
So I've crossed out this fraction because 5 is a smaller number than 10, whether it's worth that or not. So you cross out the fraction which looks like it has the smallest bottom. Okay. What do I want on the bottom to make this question work? Well, I need a 10 because that's what's on the other side. I need a 10. That's what the other fraction has, so that's what I want. So I've crossed out the fraction that was not working. Well, I've crossed out the one with the smallest bottom, what looks like the smallest bottom, and I've put what I want. I want it to be in tenths, so that means our answer can be in tenths. Some tenths plus 3/10, and then we'll get our answer, won't we? So what do I do to this fraction at the front here? What do I do to this fraction here? I change fifths to tenths. I'm just going to go through my 5 times table. 5, 10... That goes through 2 times. I counted that on my fingers. 5, 10, I ended up with 2 fingers. It means I did 5 times 2 to get 10. So on the top, I do 2 times 2 to get 4. So basically I doubled the bottom number and I doubled the top number. It's like if there was a brother and sister who slept in bunk beds, or a brother and brother, or sister and sister who slept in bunk beds. If the top bunk gets given some chocolate, the bottom bunk wants some chocolate as well. You always want things to be fair, don't you, with your siblings, with your brothers and sisters. If they get something, you want to get it. So with the bottom, if the bottom gets multiplied by 2, which it did, the bottom was times 2, then the top must get multiplied by 2 as well to keep things fair. What we've done here is we changed 2/5. We got rid of 2/5, crossed out, and we change it into 4/10 because that's an equivalent fraction. That's a fraction that's worth the same. It's worth the same, it just looks different. So 2/5 becomes 4/10. Why? Because now we've turned this into the easiest question in the SATs. We can do 4/10 plus 3/10 and we can get our answer because it's 7/10. 4 plus 3 is 7. Let's do 2/3 plus 1/9. So looking at this question a little bit faster this time. What's the problem? The bottoms are not the same. Houston, we have a problem. The bottoms are not the same. I cross out the one with what looks like the smallest bottom. What do I actually want on the bottom? I want 9ths on the bottom to make this question easy. I want it to be easy. What do we do to 3 to get to 9? 3, 6, 9. I counted 3 fingers. I multiplied it by 3. So I'll also multiply the top by 3. 2 times 3 is 6. So we didn't like 2/3. We crossed it out, made it 6/9, an equivalent fraction. Now it's the easiest question in the test. 6/9 plus 1/9 is just 7/9. As long as you can do 6 plus 1, you're okay. So let's do another 3 examples, starting off with easy fractions. 3/4 plus 2/4. The bottoms are the same, so the answer is going to be in quarters. 3/4 plus 2/4 is actually 5/4. That's not a top-heavy fraction, but we'll talk more about that later. B is going to be what I call a medium level for these questions. 3/5 plus 3/10. Houston, we have a problem. The bottoms are not the same. The one with what looks like the smallest bottom gets crossed out. What do we really want on the bottom? 10. What did we do to 5 to get to 10? 5, 10, times it by 2. So times the top by 2. 3 times 2 is 6. 3/5 became 6/10. Now we have the easiest question in the SATs. 6/10 plus 3/10 is 9/10. And then part C, this is a little bit more difficult. You have something like 2/3 plus 3/4. We have a lot of problems here. So, Houston, we have a problem. The bottoms are not the same. Cross out the one with what looks like it's got the smallest bottom. And then I go 3 to 4. So what do I want on the bottom? Really, I want 4 on the bottom, don't I? So how do I get from 3 to 4? 3, 6, 9, 3, 6, 9. I can't. It doesn't work. When I say my times tables, it doesn't work. So it means I can't actually put 4 on the bottom for this question. So this is why it's a harder level, this question. What are we going to put on the bottom? When this happens, you need to cross out both fractions. And what goes on the bottom is something that 3 fits into because of this fraction, and something that 4 fits into because of this fraction. So what we're going to put on the bottom, the easiest way to do it is just do 3 times 4. Multiply those bottoms together and you get 12. So we actually want 12 on the bottom this time. We've got to change both fractions into something with 12 on the bottom. So what goes on the bottom is 12s, and then I say one side at a time. So let's do this side first. What do we do to 3 to get to 12? 3, 6, 9, 12. My fingers are saying 4. I'm counting on my fingers and it's saying times 4. So I times the top by 4. The top and the bottom both want the same things done to them. So 2 times 4 is 8. So 2/3 has become 8/12. On the other side now. Don't need that. What do I do to 4 to get to 12? 4, 8, 12 times by 3. So also times the top by 3. 3, 6, 9. 9 on the top over here. Finally, after a lot of effort, because this is a difficult question, there's no easy way of doing this, it takes a few steps. I finally got 8/12 plus 9/12. It's the easiest question in the SATs because they're both in 12s. 8 plus 9, as long as you're careful with that, you'll be all right, and it is 17/12. Another top-heavy fraction. Another 3 examples very quickly, but we'll do minus this time because we didn't do much minus, but it's the same method. First of all, the easiest questions. 5, 6, take away 2, 6. The bottoms are the same. So we can do 5 take away 2 is 3, 6. I call that the easy version. Let's do minus fractions with a medium version. Something like, What could we have? 3/4 take away 3/8. Houston, we have a problem. The bottoms are not the same. Cross out the one that looks like it's got the smallest bottom. What do we really want on the bottom? 8 would be nice, wouldn't it? Because then they'd both be 8. So we doubled the bottom here. 4 went to 8, so we double the top. 3 goes to 6. Double means times by 2. 4 times 2 is 8. 3 times 2 is 6. So we change it to 6/8. 6/8 take away 3/8 is 5/8. And then another example of the harder version of these questions. Something like 2/5 take away 1/4. Houston, we have a problem. The bottoms are not the same. Cross out the one that looks like it's got the smallest bottom. What do we really want on the bottom? Probably 5 would be nice. The other one's got 5. But when I start counting in 4s to get to 5, it goes 4, 8, 12, and 5 is not there. And that means it's getting confusing. Something's gone wrong. Well, it should be confusing because it doesn't work. We can't put 5 on the bottom. So you have to cross out both fractions in this case. You're going to have to cross out both fractions this time. What do we want on the bottom? Well, if I times the bottom, 4 times 5 is 20. Could be 20. Is 20 in the 4 times table? 4, 8, 12, 16, 20, yep. Is 20 in the 5 times table? 5, 10, 15, 20, yep. You need to have a denominator which 4 and 5 both fit into equally. And that's why we've ended up with 20. One side at a time now. What happened over here? I'm going to count in 5s to get to 20. 5, 10, 15, 20. It is 4. So we times the bottom by 4. The top bunk wants to be times by 4 as well. We've got to make it fair. 2 times 4 is 8. We change 2/5 into 8/20. On the other side, I circle it. You don't have to circle it. I just circle it to focus me on that side, the side that I'm actually working on. How many 4s go into 20? 4, 8, 12, 16, 20 is 5. We times the bottom by 5, so we must times the top by 5. 1 times 5 is 5. We have 5/20. Now we have 8/20 minus 5/20. Make sure you remember it's a minus question this time. 8 take by 5 is 3. The answer is 3/20.
Now, as you know, that there's never only one way of working things out, and whenever Mr. Sewell and I find that we have differences, we always kind of give each other the opportunity to use our own methods of doing that. So I just thought I'd give you 2 questions of the way in which I'd probably do it at school, and maybe you'd probably see it at school yourself. 2 over 5 plus 6 over 10, we're going to start off with. We understand that because the denominators are not the same, I'm going to underline them, 5 and 10, we know that this is not a question that we can do without ensuring that both of them are the same. If they're both the same, we know then that these numerators will be the same size if you're thinking about a piece of cake, and that's how we're going to be looking at it in this way. Now what I do is I put my fraction sign in, and I know that I'm going to want to put in the same amount over here. But what I need to identify it with is, first of all, can one number go into either of these 2 numbers? Well, yes, 5 can most certainly go into 10. How many times can 5 go into 10? It can go in twice. So therefore, I can go 5 times 2, which will give me my answer of 10. Now, once I've done that, I like Mr. Sewell's very good analogy with bunk beds. I can't just multiply this by 2 and leave that and make that 2 over here. I need to multiply the 2 by 2 as well. Therefore, I will get 4 out of 10, or 4 over 10. 2 over 5, 4 over 10, that looks about right. Now let's go over to this bit over here. I hadn't had to do anything to this 10 over here, so I can just write the 10 over there, and I didn't need to multiply for anything by the 6 either, so that would continue as 6 over 10. The final bit, nice and simple, is I got 4 plus 6, which I'm going to write another new color, is 10 over 10. Now 10 over 10, well, you should know, is 1 whole. We have 10 out of a possible 10. If you got 10 out of 10 for a test, you got all right. 10 over 10 is equal to 1 whole. What happens if you get a number, like Mr. Sewell says, the C question, the slightly more challenging one? Well, I've given you 8 and 7 as denominators, 8 and 7, which clearly wouldn't be able to go into each other with face value. So we're going to look at how we could possibly make sure that both of these numbers have something to go into. What I would do is I'd do my 8 times table, my 7 times table, just to ensure that I don't find anything in between. So 8, 16, 24, 32, 40, 48, 56. 7, 14, 21, 28, 35, 42, 49, 56. Well, as you could probably hear, I noticed that both 8 and 7 go into 56. How can I make sure I know this? Well, if I times 8 by 7, I would get 56. So usually when you're really struggling, you really can't find the denominator that both numbers can go into, I would just multiply the two denominators together and you'd probably find the answer. So in the end, both denominators have 56, and I can continue my question. I'm going to go in green on this side over here. What did I have to do to that 8 to get to 56? Well, I had to multiply it by 7. Mr. Sewell's bunk bed analogy, which is fantastic. I can't just multiply the 8 by 7. I also have to multiply this 7 by 7, which gives me 49. Now that I'm ready to go on to the next one, I'm just going to change the color so it's nice and clear. What did I do to the 7 over here to get to 56? Well, I multiplied it by 8. If I multiply the bottom by 8, I've got to multiply the top by 8. You're right. 4 times 8 equals 32. I always say whatever you do to the bottom, you have to do to the top. And finally, we're going to add the two numbers together. 49 plus 32. I'm not 100% confident, so what I'll do is, it won't kill me just to calculate the answer at the bottom. 9 plus 2 is 11. 4 plus 3 is 7 plus 1 is 8. And that gives my answer of 81 over 56. Now, this is, of course, an improper fraction. An improper fraction is when the numerator is larger than the denominator, and therefore we need to convert it into a mixed number, whereby we use whole numbers. That will be in another video. Don't worry about that for now. As long as you're getting this process, Mr. Sewell and I's methods are very, very similar, but they have slight differences, and I'm sure you'll be able to add and subtract very, very easily now.